All right, everyone, let's get started. So today is a super important day in terms of the material. It's where we'll really get into some core machine learning ideas. And it's in some sense a mathematical understanding of the ideas that we have been talking about with model order selection. So just to sort of summarize, we had been looking at polynomial regression, where we have to choose the degree d of the polynomial. And we saw that in our demo that choosing d too small caused underfitting, choosing d too large caused overfitting, and that we came up with several ways to choose d by minimizing the test mean squared error through cross-validation. So that is, you train on some subset of your data and you test on a different subset of your data. You can look at mean squared error or RSS or whatever, but somehow you use that test, not the training, to make your decision about the model order. We talked about various ways to do the cross-validation, like simple splitting, k-fold, one standard error rule, all that stuff. Okay, but the stuff we've been talking about is not just about polynomial regression. It's a much bigger topic than that. So in general, models that are too simple will cause underfitting. Models that are too complex will cause overfitting. And the complexity of the model can be adjusted or optimized by minimizing the mean squared error. But I just want to make one important little modification to the slide right now, is that this mean squared error that we're going to start talking about is going to be a statistical mean squared error. In other words, it's going to involve random variables rather than just deterministic lists of numbers, which was the case for our mean squared error until now. It was based on RSS divided by n, which is like a sample average. So we're going to move from sample averages to statistical expectations in just a moment. So that will be a lot about today's concepts. But what this will give us, looking at this statistical mean squared error, is that we're going to come up with a really important equation called the bias variance equation, which will basically decouple the mean squared error, the thing we care about, into three different terms that will help us to understand what's going on much more effectively. And second, we'll see that there's going to be a trade-off, fundamental trade-off between bias and variance that we tend to experience. And this will be something that we will use to guide our intuition for the remainder of the semester in terms of choosing parameters. We'll often come back to this notion of, does it make the bias better or worse? Does it make the variance better or worse, etc.? Okay, so that's sort of a preview of what we're going to do. So, sorry, this is kind of a busy slide here, but this is trying to pack in a bunch of review material, prerequisite material on random variables. So basically, and I'm assuming that you guys have seen this before. If this certainly wouldn't be appropriate if this is the first time, because there's a lot of stuff here. But so randomness is a super useful concept in engineering because it basically can tell us what might happen when there's many possible things that could happen. And so that's really useful for machine learning experiments. So different from a typical variable, when we think of a typical variable, it's going to take on the value of some number, some fixed number. But a random variable is like a quantity. You can almost think about it like a big bag of marbles or something. It's a quantity that can generate many different possible values. So like just this marble bag analogy, like we have a bag of marbles. Each marble is labeled with a number. When we talk about this random variable, we're really talking about the whole bag. And so what that random variable can do is it can generate marbles. Like we can pull out marbles on the bag, and when you look at the numbers on those marbles, you'll see maybe some sort of pattern. Like it's always 0 or 1, never anything else. That will be one possibility. Or maybe a different bag of marbles has real numbers that have a bell curve, Gaussian distribution centered at 0. That's another kind of random variable, another kind of bag of marbles. So that's just sort of what random variables are. They're not just a simple number. They're like a whole possibility of numbers. And there's terms of terminology, when you talk about pulling that single marble out, we call that a realization. That's just one example of that random variable, and that thing is going to be deterministic. It's like 1 or 0 or whatever that number is. So that's just a little bit of terminology. Now, there's two different types of random variables, and we have to treat them different in terms of the math. There's discrete and continuous. And the discrete random variables are what we get when this random variable takes on values from a countable set. So what I mean is, in this particular case, this random variable A can take on one of k possible values, like maybe 0, 1, 0 and 1, let's say, 2 values. So that would be an example of a discrete random variable. This is going to be very important when we work with categorical quantities, because there's going to be a finite number of categories. And it's especially important when we will talk about classification in a couple units, when the targets are just one of several possibilities. They're not real numbers like we're working with now in regression. Anyway, so when we work with these discrete random variables, when we want to describe them, we have to talk about the probability of each one of those k different possibilities. So for example, let's say I have just the numbers, or let's say I have cat and dog as two possibilities of this random variable. So for me to tell you everything about the random variable, I just then need to tell you what is the percentage that it shows up cat, what is the percentage it shows up dog. That's like a full categorization or just description of this random variable. So this vector of probabilities, it's going to be this boldface P sub A, this guy. So each one of these numbers is the probability that this happens. So if I have two numbers, the first one tells me the probability that it's a cat. That probability has to be between 0 and 1. Right? Otherwise, it doesn't make sense as a probability. And, so that's one rule about those numbers. Secondly, they need to sum up to 1. So the probability of it being cat or dog together is 1. Right? If one of them is 25%, the other has to be 75%. So that explains this. So whenever you have one of these discrete random variables, you can describe it fully by this thing called the PMF, probability mass function. It's just a vector of probabilities that are all between 0 and 1, and they sum up to 1. So that's really all we need for discrete random variables. In this unit with regression, we're going to be focusing more on continuous random variables. And they take on an uncountable number of different possibilities from the set of real numbers. So when you think of like a Gaussian random variable, that would be an example of one of these. It can take on any number, all the way from minus infinity to positive infinity on the real line. By the way, I should point this out. In these sort of summary slides, I'm using capital letters for random variables and small letters for non-random variables. So if you'll notice, this A is random, but then these possibilities, these are non-random. These are just numbers or categories or something. Okay, so here again, we have this continuous random variable taking on uncountable number of values. So now the question is, well, how do I describe it then? That's a lot more complicated than this discrete random variable here. So there's basically two ways to do this. The more general way is to work with this thing called the CDF, cumulative distribution function. And that thing is defined like this. This is basically the probability that the random variable, capital A, is less than or equal to some fixed number, and that fixed number is something you use to index this function. The way we're going to focus mainly in this class on the way we're going to describe them is using the PDF, which is going to be the derivative of this CDF. So the PDF is our main tool to describe these continuous random variables. You can think of it kind of like a histogram. It sort of shows you the spread of values and how often they can happen. And it's analogous to a continuous version of this PMF. So these are going to be the main things we work with. And it's possible to connect the CDF and PMF also in this way. This is just a definition. And yeah, so other important properties of this PDF, it must be non-negative and it must integrate to 1. So similar in spirit to this, but slightly different. Okay, and like I mentioned last time, all this stuff, I tried to write this out in a really nice, simple way in this document, which if you click on this, it will take you to the GitHub repo. Okay, and also I'm going to try to focus on what really matters. There's definitely tons of interesting math, but I don't want you to get caught up in that. I just want to focus on what really matters for us. So one of the things that really matters for us is this concept of expectation, which is just the statistical average. That's all it is. It's a way of talking about average, but when you're working with random variables. So it's different from our sample average, which doesn't work on random variables. That just works on a set or list of numbers. This thing works on random variables. So the way that it works is, let's say that I have a discrete random variable. So the definition of this statistical expectation, I'm going to sum over some index k. And here I'm trying to be general. I'm looking at the expected value of some function of that random variable. That function could be like the squared value or the absolute value or whatever. Or it could be trivial. It could just be, nothing. I'm just looking at the expectation of a. So what you do is you copy that function over here. You insert this quantity, which if you remember, this was the kth possibility. And then you insert the probability that kth possibility happens. So these were the two sort of key quantities we used to define that discrete random variable. So that's essentially what expectation is. So like if you're looking, again, maybe you have the numbers, A takes on the numbers 0 or 1, and you're wondering what's the average value of A, then you're going to, in that case, F is just trivial, so you can kind of ignore it. You would then plug in 0 or 1 in the sum, and then you just need to look at what is the probability that it's 0, what is the probability that it's 1. And you add up those two terms and you get the average value of A, just as an example. Okay, now, if I'm working with a continuous random variable, not surprisingly, I need to replace the sum with an integral. So now we take an integral over the whole real line. We have function of little a. Little a is just going to be the dummy variable of integration. And now I'm going to have the PDF of the random variable a evaluated at this dummy variable a. Okay, so here again, a is just like the possibility of what can happen. And we're looking at all possibilities from minus infinity to infinity. And this describes the random variable fully. This is its PDF. This is a whole function over all the different possibilities of A. Okay. And from this, as we'll see, you can get things like the variance of the random variable and et cetera by looking at like squared or absolute value or whatever. There's obviously many possibilities for looking at different F. And so far, we're just looking at scalar random variables, this is just a single scalar number. Later, we'll need to think about collections, lists of these things, vectors of these things. Conceptually, it's very similar. So I'm not going to get bogged down with the details. Okay, so now there's two really important properties of expectation that we are going to use over and over. And this is what they are. The first one is a linearity property, and the second one is an independence. So I'm going to let you guys tell me, for those of you who are maybe able to remember some of this stuff. Let's say I have some deterministic scalars, C and D. I have a random variable A and some deterministic function. If I look at the average value of C plus D times FA, how can I simplify this?
Generic expectation, you can take the constants out of the
Right,
expected value.
exactly. So we can essentially slide the expectation through the constants. And you can maybe one way to say it is, I can look at the expectation of C plus the expectation of this. But because C is deterministic, the expectation of that deterministic thing is just that thing itself. So that's just going to be C. So the next term is going to be D times the expectation of whatever function of A we're working with. So this is the linearity rule. And this is actually pretty easy to prove to yourself if you want to do this offline. You just take this expression, you plug it into this definition of expectation, you work with the integral, simple calculus, and out will pop this expression. So you can convince yourself that yes, this is true just based on the definition of expectation. And of course, you need to work with the appropriate one, whether you're dealing with discrete or continuous. Okay, so we're going to use this a ton. So we'll see it over and over again, get some practice with it. Any questions on the linearity part? Okay, the next one is when we're working with two random variables, we'll call them A and B. You can see they're both capital. And let's say we have two functions, f and g. They can be anything, just deterministic functions. And we're going to assume this important thing, the important property, that these two random variables are statistically independent. In words, that sort of means like if you know the value of one, it doesn't help you at all in figuring out the value of the other. They're just completely independent. In terms of the math, you could define this joint probability density function and find that it factors into the product of these two individual so-called marginal PDFs. So this is the kind of decoupling you get with independence. So again, for those of you who remember some of this stuff, do you see a way of simplifying this expectation of the product? What can we do here?
Multiplication of each expectation.
Yeah, we can say this is the multiplication of the first, expectation of the first times the expectation of the second. So we get expected value of FA times the expected value of GB. Okay, so now a warning about this is if A and B are not statistically independent, then you cannot do this. You're not allowed to do this. So like one extreme example of that would be where A and B are the same. Whatever happens to one happens to the other. In that case, you can maybe see that the expectation of A times A, or A squared, should not be the same thing as the expectation of A times the expectation of A. In other words, taking the expectation of a squared quantity is not the same thing as taking the expectation and then squaring it. We saw a lot of stuff like this when we worked with sample averages. All the same intuitions work with statistical averages. Okay, so all right, any questions on that independence property? Okay, so let's talk about the variance, which is another important thing. We have expectation and variance. Variance is, we can relate it to expectation as follows. It's the expected value of this squared quantity, which is A minus its mean, or expected value of A. Okay, so this is conceptually the same way that we defined variance when we talked about sample variance and sample mean. In that case, this E was just an average, it's 1 over n times the sum of n things. This was an average, this was an average, but conceptually works the same. And in fact, we did another thing that we found very useful for our derivations, which we can do here as well. We can write the variance as the expected value of this random variable squared minus the expected value of that random variable quantity squared. We did the same thing, if you remember, with the sample averages. And so one way to use this is to move this quantity to the other side and say that whenever you have a derivation and you find you're looking at the expected value of a squared, you know that that is the variance of a plus the squared mean of a. And we'll see that show up in just a moment. Okay, so any questions on anything so far? Okay, hopefully this is somewhat familiar to you. One last review slide on something called conditional expectation. So conditional expectation is kind of like if I say, what's the probability of it raining in Columbus, Ohio? You know, some number, maybe like 10%. Like at any given moment, if I say, is it raining? Maybe it's raining 10% of the time. Probably less, but whatever. Now if I say, what's the probability that it's raining given that the sky is gray? That would be a larger probability, right? So there's some additional information that you're so-called conditioning on. Conditioned on that it's a gray sky, larger chance of it raining. So that's the idea here. So you have two random variables, and you have this bar notation. So you're saying, what's the average value, statistical average of this function of a, given that some other possibly related random variable, b, capital B, takes on the specific value, little b. So in my example, b, capital B might be color of the sky. Little b would be gray. Sky is gray. And then maybe this FA has something to do with, you know, is it raining or not? Something like that. So that's the notion here. And this is going to be super important for us. Sometimes we're gonna freeze something in our simulation and ask, when that's frozen, how does this other stuff behave? And we'll see an example just in a moment of that. So that's where this freezing is kind of like saying, this thing that's random, I'm going to fix it at some particular value, and then I'm going to see what happens to other quantities in my system. Okay, so that's conditional expectation. And let's look at the mathematical definition, and this is going to be the version with the integral. There's a similar version with a sum for discrete random variables. So we have an integral. Just as with standard expectation, we have function of a, but now, rather than using probability of a, we're going to have the conditional probability, this thing over here, which is, or probability density of a given b, which is going to depend on two particular values. The b is the one I'm fixing on the left, and the a is my dummy variable of integration. So what happened when we added this conditioning is that we added this conditioning over here. Okay. And this might seem abstract now, but we'll start using it in just a moment. Okay, so any questions so far on conditional expectation? Okay, so now another thing that you'll often see is here we're freezing this variable b, capital B, at a very specific value, little b. But sometimes we don't want to freeze it at little b. We sort of want this to be general. In some sense, we can, if I don't freeze it at a particular value, this thing stays random. And what that means is that, okay, if I didn't have any conditioning here, and I look at the average value of this function of a, I get a value with no more randomness, right? I'm looking at the average thing that happens. That's just deterministic. There's nothing random about the average value. But now if I say, let's look at the average value given some random variable b, and I keep b random, that means this whole thing is a function of b. And so because b is random, this whole thing is random again. So if I want to know like what happens on average for this when I look at different b's, here's an example. This is looking at the average value of a given b, but B is random. And then you say, okay, I want to know what happens on average for different Bs. I can do one more expectation on the outside. That expectation here is taking the variability of B out of the question. This one is taking A out. And when you're all done with that, this guy is no longer random. But what's interesting is that the variability of B goes away completely. So this is called the law of total expectation. There's a short proof of that in here. And we'll see that this is used when you have several different kind of moving parts and you want to one by one take out the randomness because that's easy to derive just one by one. This allows you to do that rather than dealing with many things simultaneously. Okay, so so those are kind of the main points. So again, I realize this might be kind of abstract. Hopefully it's jogging some memories if you haven't thought about this stuff for a while. But we're pretty much ready to use it, and I think at that point it will start to make more sense. All right, any last questions before we move on? Do you guys have a question over there? I'm happy to answer it.
We're just filling them in on what you're talking about.
Okay, yeah, because often when one person has a question, a lot of other people have the same question, so don't feel bashful to ask. Okay, so let's see how we're going to use this. We're coming back to machine learning now, and this is something that we saw in polynomial regression, but here we're making it a little bit more general. So imagine that we have this true model. This is what's actually happening and generating our data. And it goes like this. There's some targets, y. They're equal to some function of a vector of parameters x. So like we saw before, maybe the x's are different powers of some scalar x, and this is summing them, or there's different possibilities, But we saw an example of this where this was like a polynomial on some scalar x. And then there's some random noise epsilon being added. And so this is just kind of a simple model, but it helps us separate some randomness here from some like structural stuff going on in our modeling. So let's talk a little bit about how we're characterizing these random variables, or all the different variables. So this epsilon is going to be some noise. We're definitely going to think of it as random, and we're going to think of it as having a mean of 0. So on average, it's 0. This is, by mean, we mean the statistical expectation, and some variance of sigma squared. It might be Gaussian, but that's actually not, we don't need that for anything. And we're going to assume that it's independent over draws. And what I mean by that is maybe we're using this model to generate our training data, so we're going to be using this model again and again and again. In other words, this might be one set of training features. This is a training target, and then I'm going to have some error for that. And now I'm going to have another set of training features, another training target, but that error I'm going to assume is statistically independent of the first error, and so on. Generally speaking, when you work with noise, you just assume it's very random. It's random across just, almost all the ways you can think about it. Okay, so what about x? So these feature vectors, we're also going to think of them as random. And if you think back to our experiment, I'll just show you maybe a picture of our polynomial experiment. When we ran this, we were drawing random values of x on the horizontal axis, right? Uniform distribution. So already there, we were thinking about those things as random. And that's all I'm doing over here, as I'm just saying, yeah, think about those feature vectors as random, independent over draws. So if I have like a whole data set of many different xi's, x sub i's, then it's independent over those different i's. Also, I want to make sure that my features are always going to be independent statistically from my noise. They're just totally decoupled. Knowing the features doesn't tell me about the noise and vice versa. And we're going to use this model to generate our data, both for our training data, as we know that's when we have little i's under everything, as well as test data, which is data that we don't have at training time, but sometime after I'm done training and I want to use this model in the real world, there's going to be some feature X. I'm going to assume there's going to be a true target Y out there as well as a true noise epsilon. And eventually I'm going to care how well my model trained on this works on this test data. Okay, so these are all the assumptions we need on the true model that is responsible for actually generating the data that we see in our machine learning experiments. Okay, now, separate from that, we have a prediction model. We're going to call that F hat. So the prediction models that we've seen so far, we've focused on models that are linear in some coefficients beta. That's been important for us. The model doesn't necessarily need to be linear in X. It could be, but we saw polynomial in X. That's fine. But it's important to remember that this F and this F, generally speaking, don't need to have anything to do with each other. Maybe in the real world there's some very complicated function, but then I just come up with some simple linear model. Right? So we're allowing these to be maybe very different. Anyway, I come up with some function F hat. It's driven by some parameters beta hat. But as we know, we can train those parameters based on training data. So we collect a bunch of training data, XY pairs, that were generated by this model, and we go through our least squares training procedure. Finally, we get a beta hat, and we plug that into this predictive model. And now that it's there, and someone gives me a new test X, I can plug that into the model, and I'll get a prediction of the true test Y. Probably won't be perfect, but it's a prediction. And that's my prediction model. So we have a true model here, prediction model. Now, important thing to note is this beta hat is actually random. That's because I computed it based on training data, and I said that the training data, I'm going to think about that as random. So another way to think about this is imagine that I'm running an experiment over and over again. And this is something we can do in software, but like every time I run the experiment, I draw a new set of test data from this model. Maybe the model has a uniform distribution, a Gaussian distribution. So every time I run my experiment, I get a whole new set of data. Based on that set of data, I can fit beta hat. But since I'm going to be doing this over and over in different experiments, my beta hat is going to be different every experiment. And in the end of the day, you can think of that as a random variable, a random vector as well. You can think about its mean, its variance, or the covariance matrix, and so on. But the important thing here is to remember that this beta hat, the trained version, is actually random as well. So there's a lot of randomness going on, and that randomness, as we'll see, is key to understanding what's actually happening. Okay, any questions so far on the setup? So this is the setup for our model. Now, how do we measure performance? Since we're working with regression, we're going to work with mean squared error. It's the easiest thing to work with. And the mean squared error is this. Okay, so what you do is you're looking at the average value of the difference between the true target and your prediction. And these are not test quantities, not training quantities, these are like the test quantities. But notice I'm going to condition on X, which means even though X is random, I'm going to, for this purpose, freeze them. Pretend okay, what if X takes on a particular vector? And now I can tell you what is the mean squared error on my estimate Y hat for that fixed value of X. In other words, maybe the test feature happened to be 0.5, and I want to know for that exactly what is my mean squared error. Or maybe it happened to be -1. What is my mean squared error then? Those are going to be different mean squared errors. They're going to depend on the value of X, my test feature. So it turns out that's going to be how we do our analysis because it's going to be tractable. And another way to think about what's happening with the averaging here. Averaging is it's it's taking out randomness. So this expectation is taking out the uncertainty that we have about y and y hat using some integrals. But as a result, it's not removing any uncertainty about x. So I could think about x as a fixed vector and plug that in. Or if I want, I could think of x as a random vector, in which case this whole thing becomes random. So we'll see some examples of this if that sounds too abstract in just a moment. Okay, and then, okay, so y, this variable y, it's random for what reason? Well, it's random because of noise, variabilities in noise, and variabilities in features. Now y hat, why is that random? Coming back to that model, it's random because of, well, actually, because I'm conditioning on x, when I think about the randomness in y, I'm gonna treat this as fixed, and all the randomness will come from just the noise. Sorry, I misstated that. And again, because I'm conditioning on x or holding x fixed, when I think about the variability in y hat, it's only coming from beta hat. Okay, so we'll see why this is all important in just a moment. But that's the statistical model. And all right, any questions on the model or yes?
The y is the test, or is it the
Yeah. Yeah, so these guys are test quantities, and then the training will always have those subscripts I on them. Right, yeah. We always care about how our model works on test data. Training data, as we saw, if you just look at the training data, it tells you the wrong thing. It's overly optimistic. We need to look at test data independent of our training data. Cross-validation. Okay. Okay, any more questions? Okay, so let's dive into this. It looks like a crazy derivation. As you'll see, it's not actually that crazy. It's not too bad. And we'll get to practice a little bit with our main expectation, two expectation rules. So, and the result is super important. So just bear with me. And let's just start out by saying, what are we doing? We're trying to come up with a meaningful way to look at this mean squared error. This is the thing we care about. We care how well we can predict the target in terms of average squared error, and I'm going to focus on for a fixed value of the test features x. Okay, so by definition, we just saw this is how we define our mean squared error. Okay, so the first step, all I have to do is plug in the model for y. That's this model from the previous page. It's this structural thing happening to x plus random noise. And I need to stick in my model for my prediction y hat. That's just my f hat. Okay, so that's that. Now we have to go to work and somehow simplify all this. So the first step is going to be to expand this. Think about it as a quadratic. Think about it as a sum of two things, epsilon plus this squared. So what we're going to do is we're going to just expand that quadratic. So we're going to look at epsilon squared, that's this term. This quantity squared, that's this term. And the cross term, we're going to have 2 times this times this. Okay? So that's just simple algebra. I've just expanded this. All inside this expectation. Nothing crazy yet. So now I need to simplify this. So what can I do to simplify when I have expected value of a sum of things? Linearity. Expected value of the sum is the sum of the expectations. So it's going to be the expected value of this plus the expected value of this plus the expected value of this. And to be careful, these are all conditional expectations. So I have to carry that over when I'm doing my derivation. I always have to have that bar x. Otherwise, actually, the quantity, once you get rid of this, in some cases, the meaning, the value changes completely. So it's important to keep that there. Okay, so finally, the first one is expectation of this, given x. Then we have this sort of cross term, and then we have expectation of this. So let's let's take a look at this cross term. This is the most interesting one. So I'm looking at the expectation of this. Now, as you can see, it got split into a product of two expectations. Why could we do that?
Independence.
Independence. So exactly what was independent?
Epsilon and
Yes, epsilon and
beta and x.
beta hat. X is deterministic because we're conditioning on it. So think about x as, for this expectation, x is just a fixed value. So the only thing random here is epsilon and beta hat. But as we saw, or just kind of intuitively, beta hat is all from the training quantities. Epsilon is from test. Training and test are independent. So that's why these are statistically independent. Okay, so that allows us to say expectation of this is expectation of epsilon, and of course condition on x, that's this, times expectation of this second thing, condition on x. Okay, is everybody good with what we did there, or any questions? Okay, next thing is this goes to 0. Why does that go to 0?
0 mean.
0 mean, yes. There's one more kind of technicality we should probably talk about.
They are independent. Epsilon.
Yeah. So because what we're saying here is that if you tell me x, then what is the mean of epsilon? In this case, because x and epsilon are statistically independent, you could basically say, well, telling me x doesn't really change what epsilon is, so I can just kind of forget about it, and then I just care about what is the mean of epsilon, and if you remember, we assumed it had mean 0. Okay. If you want to be more technical about it, it's possible you go back to your definition of conditional independence, you plug a bunch of stuff in, and you convince yourself that yes, when these are statistically independent, then the effect of x will vanish from that integral, and you're good. Okay. So we won't do that now, but you could do that if you wanted. Okay, so that got us to this line. And are there any lingering questions about this line? Okay, so now let's tackle this first term. So why is the expected value of epsilon squared given x sigma squared? Okay, let's do the first things first. Does this have any bearing on the calculation? No. So just forget about that. Because x and e are statistically independent, it's just a distraction. So why is the expectation of epsilon squared equal to its variance?
Because it's like saying epsilon minus epsilon mean all squared, that's mean is 0.
Yeah, so let's come back to this. This is one of these instances where we have this in our derivation, and we want to relate it to the statistics of A, and we see that average squared value is the variance plus the mean squared. Right? By moving this over, you can see that this is equal to this plus this. And we know both those. We know the variance of A, that was variance of epsilon, that was sigma squared. We know the mean of epsilon was 0. So that's why this whole thing doesn't matter. And the expected value of epsilon squared is its variance. So that's what happened. Here we are. So that's a common thing that happens is you'll see this in a derivation, and you need to write it as the variance plus the squared mean. All right. Is everybody good at that? Okay, so what else do we have? So then this whole term went away because of the 0. And then we have that second term. That's going to be the challenging one. So we're going to do a little trick. It's not obvious maybe why we're doing this trick at first, but it should be helpful later. We're going to subtract a quantity and add the same quantity. So we can do that because this whole thing is 0, right? And I can always insert a 0 anywhere. It doesn't really change anything. So we're going to insert this 0. But the reason why we're doing this is it's going to really simplify our derivation. We're going to think about this as one term in this quadratic, and this is a second term in the quadratic. And then we're going to expand the quadratic again. So we're going to have the first term squared. That's going to be this term squared. We're going to have the second term squared, which will be this guy. And notice that both of these are inside this expectation. So all we're doing is algebra, not more than that. And then there's the cross term. So we're going to have 2 times the expectation of this times this. And that's what we have down here, except we did a little simplification. We actually slid that outer expectation all the way through and didn't compute the expectation of this. So why could we do that? So what's the property that lets us slide something through an expectation?
Because they're deterministic.
Yeah, if it's deterministic, like a constant, I can just slide it through, right? So is this deterministic with regard to this expectation given x? You just have to look like, is there anything random about this? So x is fixed because I'm doing this given x. Right? So x is fixed, so this is definitely deterministic if x is fixed. What about this quantity? Yeah. So this quantity is dependent on x, but x is fixed. And then there's this randomness in this beta hat, but this expectation sort of removes that randomness. So basically this guy, yeah, this is deterministic, so I could pull it out of the expectation, essentially slit it through that expectation. And that let me apply the expectation to this second term. Now let's take a close look at that. So is this a random quantity or deterministic? If I'm fixing x. Deterministic. Because the randomness here is taken care of by this expectation. And now, if x is random, yes, this whole thing is random. But I'm saying, nope, x is fixed. So this is just a deterministic quantity. This guy, however, is this random or deterministic? Random. It's random because of this beta hat. That's my training beta hat, which every time I run my experiment, I have a slightly different parameter vector. So that's moving around. So, but I'm going to take the expectation of this, right? And by linearity, I can say it's the expectation of this, which is deterministic, so it doesn't change, minus the expectation of this. And that second expectation is this conditional one. So do you see how when I take the expectation of this, it ends up giving me exactly the same? And then you subtract them and it goes to 0. So basically, this second thing just disappears. Is that making sense or needs more explanation? Okay, so the nice thing is that this whole thing has gone away, and essentially we are almost done. Very last step. So here we have this first term. The second term won't change. We just have to do a little bit of simplification. So what about this outer expectation on this? Is this playing any role? So again, I'm doing an expectation but treating x as deterministic. So this is deterministic, right? And what about this? This expectation has kind of averaged over beta hat, leaving a dependence on x, but x is fixed. So nothing here is random once I fix x. So I can basically get rid of that expectation and write it just like this. Okay, so we're finally ready to make some sense of this stuff. And essentially we're saying the mean squared error can be written as a sum of 3 terms. The first is what we call the irreducible error. The second is what we call the bias squared. And the third is what we call the variance. So let me try to explain a little bit about the meaning of these things. So let's start with the bias term. So if you remember, f of x is the noiseless version of the true model. Right? F of x is not the true target because the true target has noise. But if I look at the expected value of y, because this is zero mean, or let's say expected value of y given x, that's just fx. So maybe it's more clear, rather than writing fx here, write it as the expected value of y given x. The second thing here, this is just a fancy name for y hat, this f hat stuff. So I'm just going to call that y hat. And now you can see that what's inside this square, it just means the average value of the error between the true and predicted targets. So the bias goes to 0 if, on average, your predictions are correct. Now, it doesn't mean your predictions are ever correct in the moment. It just means if you average across many, many moments, they're correct on average. So we'll see this play out in a moment, but that's how we can think about bias. Bias tells us about whether we're doing well on average. The second term tells us how is our prediction varying from its average. So maybe I'm doing the right thing on average, but every time I do something, it's very far from that average. So this is quantifying how far is my prediction from its average. And it's just, basically, if we think about this as y hat, it's just the definition of the statistical variance of y hat given x. And then there's one more term, which is the irreducible error. And the way to understand that is even if like a genie told you exactly what f was so that you would just set fx here, you're still never going to be able to correctly predict your targets because of this epsilon. There's always this random noise in your targets that has nothing to do with your features, so you can never predict it. So in the best case, you can, with y hat, you can match this term, but there will always be that epsilon left over. And the error from that is this irreducible error. It's just the baseline. There's no way to reduce it. But this other stuff, yeah, if you have no bias, you can set this term to 0. And if you have no variance, you can set that term to 0. So it turns out getting the bias to 0 is something that can often be done. Getting the variance to 0, I don't think you can do that, but you can often make the variance really small. As we'll see, if you have lots of data, maybe the variance gets really, really small. So that's this is the so-called bias variance equation, super important. And what it's telling us, again, is it's telling us about the mean squared error in our predictions for a fixed value of our test vector, test feature vector. Now, you might say, I don't really care what happens for a particular test vector. I care what's going to happen on average, because when I'm applying this in the real world, I'm not going to know what my test vector will be. So tell me the average version of this. So the average version of that would be you just take an expectation of that over x. So now this expectation is removing the randomness in that x, and we can finally just call this guy mean squared error on y hat. So this is just if you did this experiment over and over again using many different x's, and you just said, how good are my y hats? How far are they from the truth squared on average? That would be this. And so we just have to take expectations over this stuff. So we get expectation of sigma squared over x, that's just sigma squared. Expectation of the bias over x, that's this term, and expectation of the variance over x. So in all these cases, this expectation is just saying, let me look over all the possible variations in x to tell you what the average value is. Okay, so that's all the hard stuff. Let me just try to relate this back to this polynomial demo. I know it's almost time's up, but I think we'll come back here next time, but it's important just to, I think, see it now for a moment. So in this demo, in these pictures, we're going to be looking at 3 different possible model orders. The first one, d equals 1, is when we use a linear model, cubic, or high order model. So the red curve is telling us the true function, which we knew, actually there's a little typo here, this should be expected value of y. This is the true function, which, if you remember, was cubic. This is like the noiseless target function. The true targets are noisy around here, but this is the thing we're actually trying to predict, right? And so the way to think about this is imagine that I run this demo or this experiment 100 different times. Each time I generate a new training data set, a new training data set, and what's going to happen is I'm going to fit my training data, I'm going to get a line, right? Every time I do that, my line is going to be a little different. Sometimes it's going to be shifted up or down, tilted slightly differently. So I could ask the question, what is my average, the average line? If I average all those regression lines over all my experiments, that's going to be this solid green thing there. The solid green curve is the average prediction of y given x. So, you know, if you say x is 0.5, then this is the average value is here. That's what the green line is showing. This is the average prediction. And when that average perfectly matches this fx function, we would say that we're not biased. So when d equals 1, are we biased? Yes, there's a gap, right? If I said when x is 0, are we biased? No, there's no gap here, but for other x's, there's a big gap. Now let's say I increase my model order to d equals 3. Is there any bias? No. You can't even see the red, it's right under the green. It's saying that in this case, on average, we're making the correct prediction. So what's happening here is for every experiment, I am generating a new polynomial fit. But every time it's going to be a little different. Never going to be the same. So I'm showing you here, the green curve is showing you the average of all those polynomial fits. And these little error bars are showing you the standard deviation. They're looking at the square root of the variance of y bar. So if you remember, that's the square root of this term here. So the bias can be seen as the difference between the red and the green solid thing, and the variance can be seen as the heights of those, or the squared heights of those error bars. So you can see that the bias is a little bit lower here than it is here. It just turns out that way. Not the bias, the variance. The variance or the standard deviation is a little bit lower in the middle than the outside. That's what those are telling you. But we have no bias here, but we have some variance. Okay. Last case, what if I choose my model order as 14? If you remember, we saw a picture of this before. It's a crazy looking model. It might look something like this. And then the next time I do it, it might, who knows what it looks like. And then the next time I do it, it looks crazy again. What's amazing though, if you average all those crazy functions, it looks exactly like the cubic we want. So here again, our model is unbiased. The red and the green solid curves are matching perfectly. But what's worse about this, the reason why we don't want to do 14 instead of the correct model order, is you can see how much the variance has increased relative to here. Variance increased, and that is going to add to our mean squared error. So our mean squared error in these two cases, they both have the same irreducible error. They both have zero bias, so that goes away. The difference between them is all about the variance. The variance, when you look across experiments, you know, on average you're doing always the right thing, but there's bigger variation from the average here that's going to hurt you in terms of your mean squared error. Okay. Here's some other illustrations of what it means to have high bias. Means if you're throwing darts at a target. If you have high bias, it means that on average, you're away from the target. So here on average, it's great. Low variance means a tight cluster. High variance means a loose cluster. Okay, so that's we'll come back to this next time, can ask some more questions, but these are super important concepts that are going to basically guide our understanding of machine learning models from now on. We're always going to come back to think about what's the bias, what's the variance, how are those things changing. All right. See you guys on Friday.